Pleasure of welcoming Randy Grunwell, who is a native Virginian, electrical engineer, from Virginia Tech. He designed test systems for radio products. So obviously, we've got a man with a great deal of expertise. His interest in clocks came from when he found out how much it would cost to fix one of the clocks that his grandma had. I think that was $300, wasn't it, Randy? Well, Randy is not one to spend that kind of money. So he decided he was going to figure out how to do it himself. And he met a guy by the name of Tom Fowler, who's had a tremendous amount of expertise and spurred Randy's interest in watching clock making. Tom also was very interested in having Randy join the NAWCC many years ago. So he also joined a small group that has been repairing, fixing clocks and watches for years and years and years. So this group also shows people how to do it themselves and does instructive things all over the place. And Randy is an instrumental in being able to attract people to the NAWCC by doing classes and then developing an interest, particularly in young people, on clock making and watch making and horology in general. So he is a great recruiter for the NAWCC and is a man who is interested in keeping our horology interests alive. And now I give you Randy.
All right. Four right here are people from the Tuesday night clock group.
Oh, good.
Yeah, they know what they're in for, unfortunately. Okay. Go ahead and you take stuff from one writer, it's plagiarism. You take it from more, it's called research. This is a lot of research. A lot of research. Why do we have 24 hours in a day? Why not 10? Why not 100? Go ahead. It keeps going.
Oh, okay.
The Egyptians probably started it. This is a sundial. Doesn't look like a sundial, but it's a sundial from about 1500 BC, BCE, I guess. Go ahead. The way you would use it was, go ahead, keep going. Keep going. There's a little hole right there that you would put a plumb bob on. And then you would turn it towards the sun, and the shadow would fall on the length of the arm there. And that would tell you the time. Go ahead. They had 5 marks on there. They like base 10, but when you have 5 marks, it gives you 1, 2, 3, 4, 5, 6 categories. Good. So you had 6 periods in the morning, 6 in the evening. You have a 12-hour day. You have a 12-hour day, you have a 12-hour night. But the interesting thing is these time frames were not set. The times of day change during the year. These are not hours as we know them. These are kind of like, this is how much time you have before it gets dark. This is how much time you have before it gets to be noon. This is how much time, you know, it's give you kind of an idea. It's not like, oh, it is 12:35. No, it just kind of gives you a general idea. Right? Why is clockwise clockwise? That's something you hadn't thought about, had it? Right? The earliest clocks rang bells. They didn't even have faces. When they put faces on them, why did they choose the direction that they chose? One more time. It's based on sundial. The shadow of the sundial goes clockwise. When they made clocks, they made them go the same direction as the sundial. Interesting thing is, One more time. If sundials were created in the southern hemisphere, if clocks were done in the southern hemisphere, clockwise would go the other way. If you took a picture of the sun, the same clock time every day, in the same position, shaking out the same direction, what would you see? That's called an analemma. I hope I did the right wording for that. That figure 8 is what our sun does in the sky, and we don't really notice it. Go ahead. The Earth had no tilt and had a circular orbit. The sun would follow the same path every day, but you would have no seasons. Go ahead. Because we have a 22.5-degree tilt, we end up with a figure 8 type pattern. This is the height of the sun, and this is essentially plus and minus time on a sundial from what we call clock time. It's 0 at 0, right over the equator. Has the maximum min at the solstices, and the equinox is right here. Now that's only if it had the tilt and a circular orbit. Go ahead. Set that up. Next one. Now, Earth's orbit is actually an ellipse, and it causes an elliptical pattern from the sun. We're no longer, we shifted our solstices. They're not at the minimums and the maximum. It moved it. And what you can't really see, go ahead and go through that some more, is the center is no longer here, it's moved up. The reason it moved up is because of Kepler. Very many people know who Kepler is. He created a bunch of planetary laws. One of them is that the motion of the planet as it goes around the sun, the area that it sweeps is the same no matter what the period is. So when the Earth is furthest away from the sun, it sweeps really slow, relatively speaking, to get the same area as it does when it's close, relatively fast. If you think of it like a tether ball, you throw a tether ball, you do like that, and it goes round, and then it gets faster and faster and faster. And you're not putting any more energy into that tether ball. It's going faster and faster, but it's swinging the same amount of arc, the same area of arc that it did when it was going slower. That's essentially Kepler's law. Okay. And that's what you get at the end when you put the two together. The center is no longer here, it's moved up. Go ahead. Okay, so what does this mean? These are each days of the year. I've got a cheat sheet because I don't remember these things. About here, that should be February 11th. The sundial is 14 minutes, 15 seconds slow from what clock time is. When you move up, where is it? April 15th, right there. April 15th, tax day. Yeah, it's 0 offset. Your sundials are correct. Okay, sundials are always correct, but they agree. We have +3 minutes on May the 14th. You notice that the solstice is no longer the 0 point. The 0 point is September 1st. Actually, I missed June 13th, sorry, June 13th. It comes back there 6 minutes off in July, back down to zero here at September 1st. Over here, you're 16 minutes fast. And here you're at December 25th, Christmas. Sundials are okay on Christmas. So there are 4 times that a sundial agrees with a regular clock. Now, if you plot the days, go ahead, Bob. The fast and slow by day, you get this curve. This is called the equation of time. You don't run into this here that they're young. But this is what you got to offset your sundials to make it agree with clock time. Go ahead. And those are all the dates and times that I just said. Okay. Why are there 60 minutes in an hour? Go ahead. Why not 10 or 100? The Babylonians. It's all their fault. Go ahead. They've used base 60, which is a sexagesimal. And I bet you all didn't think you were going to hear about sexage here, did you?
You think it had anything to do with pulse, the 60 minutes? With personal pulse?
Probably
But
faster.
the main reason is because they use base 60. And the base 60 is really nice for the pulse. Because it's divisible by so many things.
All right,
You have to realize they didn't have calculators. They didn't really handle decimals. They
Right.
didn't do decimals, they did fractions. Well, when you get into messy things like sevenths and thirds and all this stuff in regular decimal, this one, 60 is divisible by so many things. It's beautiful. You come out with, if you round fractions, you don't have to deal with weird stuff. Then simplify the math. One more time.
Randy, you got a question? and we're giving-
You can read the history of mathematics, you find out these people
wow,
were great at mathematics.
Oh, yeah, the Babylonians and the Sumerians, yes, they really did,
And we owe all that to them.
pretty much, yeah. And the Greeks carried it through. Yep. And as you see, these are the things that, 100 is divisible by, which I can just imagine trying to do fractional addition and multiplications and all this stuff.
So we should throw out the metric system?
Metric system, yeah, that kind of, that's nothing to do with that.
Go back to imperial.
Okay. Why were Roman numerals used? And why are they still used? I mean, come on. First, English-based people doing all this.
They ruled the world.
It also.
And it didn't go off.
And this is one of the ones that got really nice and fancy with the cool little
Pretty cool.
graphics.
Do they even teach Roman numerals in school?
Yeah,
Yes.
hey, it's a new thing now.
Yeah.
Okay, Bob. Leonardo Bonacci is, the credit is given to him for bringing Arabic numbers into our world. And he did it in about 1202. Now, that's when he introduced it. It didn't become common for many a century. And by the way, Fibonacci, his name is actually Leonardo Bonacci. He's also known as Leonardo of Pisa, or Leonardo Bigolo Pisano, which translates, I think, to traveler from Pisa. He was an Italian mathematician from the Republic of Pisa, and he was considered the most talented Western mathematician in the Middle Ages. Some fellow named Guillaume Libre changed his name, which is kind of bizarre. In 1838, he called him Filius Bonacci, or Fibonacci, which means son of Bonacci. So he's Leonardo, son of Bonacci.
Did the zero come from the Arabic numbers?
Zeros do come from Arabic. Before then, they used N for null. But it wasn't really a digit, it was more just kind of a, yeah, we don't have any. Because Roman numerals don't have place digits. You didn't have a 0 in the tens column. Right? They didn't understand that. And when they decided to use that, when they learned to do it with the Arabics, they're like, well, what do you use to show that? And you use a whole, a 0. That's the placeholder, is a whole. Okay. Prior to this, Roman numerals were used everywhere. In everyday life, those were the numbers, those were the numerals that you used. Now think about that for just a moment. Your paychecks were done in Roman numerals. All accounting was done in Roman numerals. Everything was done in Roman numerals. So he's also, Fibonacci is also known for the sequence. 1, 1, 2, 3, where you start with 1, 1, add these two together, that makes a 2. Add these two together, that makes a 3, 5, and so on. That has some relevance in like photography. Your 5x7s and your 8x10s and your so on. Those are actually very close to Fibonacci sequence. It talks about a golden ratio. You take any two numbers and start it, you will eventually get to a golden ratio, which is like 1.67, I think 1.6 something, I don't remember, square root of 5 plus 1 over 2. Go ahead. Now, what happens if we were still living in a Roman world? There you go. For $9,499, you can have that car. One more time. That's your speedometer. And I would have put an odometer in there, but you don't have any idea how horrible that looks. So, there's my return address. This is my sister's address. Zip codes are particularly nasty looking.
That'd really complicate the post office.
Oh, yeah, the post office has trouble now.
Yeah.
One more time. And then there's this. Yeah, if that doesn't just send shivers down your spine, you think filling out one of these things is bad. Why do clocks need escapements? I mean, why do they have escapements? What are escapements good for? Right. This is a video from Alejandro de Maza Vivar. It's the only one I can find that actually showed a falling object. Go ahead and hit. Now it's going to go fast. Ready? He puts them on there and he has two balls. One ball is going to go forward and the other one's going to just drop. Oh, did you see it? Okay, this is slow motion and you can see at each mark where it falls. And the green one just falls straight down. It followed it, but the parabolic is easier to see. It speeds up as it falls. Well, you can't just put a cord around something falling and tie that to a hand and say, there it is, because it's going to speed up. Go ahead. What you really want is something that would fall at a constant rate. You can't do that here on Earth. Okay, next. Springs have the same type of problem. These are different torque curves. As you see, they all decrease over time. Some of them have a nice little flattish area, but generally they all decrease. Go ahead. What you want is you want to have a constant torque, but you don't have that. Okay. So then you get escapements. Escapement breaks up a falling weight. It actually stops the fall. You have a fall and it stops. You have a fall and it stops. You have a fall and it stops. That's what an escapement does. Escapement literally stops things falling, or in the case of springs unwinding. And it does it with an external regulator. Pendulums, balance wheels, and so on. And that interruption, if you do it at a regular amount of time, will allow you to do timekeeping. Okay. Same works with springs. Some escapement, some clock escapement. This is a virgin folio. Came around about 1400. Now that's 100 or 200 years after Bonacci, Leonardo Bonacci, introduced the uppy-ups with the Arabic system. So we're still not into using Arabic system in daily use. Go ahead. It's a virgin folio. I had mistaken, done in church towers. They were capital investments. These were not small machines. These were very expensive. You did not have one in your house. Go ahead. They rang bells. There was no dial. So actually, this is where you get that the clock tells time. You would listen for the bell and you would count the bells, and the bells would tell you what the clock time was. That's why you tell time. Go ahead. Okay. And they're, really accurate, plus or minus 10 minutes a day. There was I write it down. There's a quote from Chaucer from Chanticleer and the Fox. Chanticleer is a rooster. For crowing there was not his equal in the land. His voice was merrier than a merry organ that played in the church, and his crowing from his resting place was more trustworthy than a clock. That kind of gives you an idea of what people thought about clocks back then. Go ahead. This is what is actually going on. You've got your verge, and you've got your folio. The folio has weights. When you have your arms way out, you're slow. When you move them in, you go faster. Now, I made the mistake of thinking that this actually was like a balance wheel, but it's not. A balance wheel has a spring that will bring it back to center. This doesn't have a balance, doesn't have a spring. If you did not have the other pallet, it would just keep going. So actually back it up now. Watch here and here. You'll see that there's only just a little tiny bit of gap that the folio is free. Otherwise, the crown wheel is pushing on the verge practically all the time. This made for very inaccurate timekeeping, and it was very sensitive to weight and temperature and friction and everything else. I mean, it was just not the best way to do it, but it was first. Go ahead, Bob. Then you got Christian Huygens, Dutch scientist. He came up, he built the first pendulum clock. Go ahead. 1656. Go ahead. It has returned by gravity to the center. This means that the pendulum actually only had effort put into it at the extremes, and most of the time it was free floating, free flying. He managed to get it under a minute a day, and then later got it under 10 seconds a day. Which, think about that, 10 minutes down to 10 seconds. Yes, please. Okay. Right. This is a recoil anchor escapement. Most of you, I'm sure, have seen these before. This particular design is not how we see it most of the time in American clocks. they have that strap type movement or strap thing down here. But you notice that the wheel goes backward a little bit every time it engages with the verge. Go ahead. Keep going. Keep going. And as you see, there's a good portion of the swing where the pendulum is not being affected by the verge. Go ahead. And why is it called an anchor? One more time. That's why they're called anchor escapement. It looks like an anchor. Go ahead. Then you got George Graham, Richard Townley, Thomas Tompion, and George Graham. They made the deadbeat escapement. Go ahead. Keep going. It's erroneously credited to Graham. Keep going. It was invented by Townley, who was the astronomer, and Tompion, keep going. He was the mentor of Graham's, who built the first two clocks. Graham, however, made a slew of them. So Graham is known as the maker of the escapement engine. And by the way, I tried to include where I got all this stuff. Wiki is, by the way, wonderful. Thank you, Wiki. Keep going. This is a deadbeat. You'll notice very similar looking, it's an anchor escapement. It's very similar looking to the recoil, but you'll notice that the escape wheel doesn't go backwards. You'll also go ahead. You'll also notice there's these little planes back here. That's where you get the impulse to keep the pendulum going. Keep going. These are the two side by side. One thing you might notice is teeth go the other way. They're both going that direction. But one of them, the teeth are pointing that direction, the other one they're pointing away from that direction. It's strange, but that's the deadbeats go on the shorter side and the recoils go on the longer side.
They had to do is put a wheel around, didn't they?
Yeah. Go ahead. Well, that and change the profile on the verge.
Well, yes.
Keep going. Why do clocks have gears? I know that sounds like a stupid question, but why? Go ahead. Keep going. They convert power. Otherwise, you'd have to turn the clock. You have to wind it 168 turns per a week. And if it's an 8-day, it's actually 192 turns. How many people want to do that? Go ahead. Why are clock gears different than other gears? If you look up on Wiki and say, show me a picture of a gear, you get a gear that looks like these black outlines. They're stub end, they're blocky. But clock gears are like the blue ones. They got points on them, they're rounded. Why? Go ahead. The stubby gears are called involute. Go ahead. The involute curve can be made just like that. That's an involute. Isn't that neat? Mathematically, that's called an involute. It is actually a type of cycloidal, but it's instead of rolling a circle, you're actually rolling a line, which is a circle of infinite length. Go ahead. The nice thing about involutes is they touch in more than one place at a time. They're very good at power transfer. And there's a line of force that they run on. Go ahead. Keep going. It's really good for power transfer. But there's a lot of friction because you have a lot of touching, as it were. This is a true cycloid. This is called an epicycloid because it's a circle running on the outside of a circle. A cycloid merely means you're taking a circle, following a point on that circle as it traverses something else. It can be a flat surface, it can be another circle. On the outside of the circle, that's an epicycloid. Inside is a hypocycloid, just names. One more time. Does that kind of remind you of something though? Yes, a spirograph is, in this case, is an epicycloid. Go ahead. Here's the epicycloid curve. Now, this one shows a hypocycloid. This is called an addendum. This is a dedendum. Essentially, this is your pitch circle. Anything above it is add, everything below is deduct. In a clock, there's a special case where you, I wrote down what that is. If the hypocycloid is half the diameter of the pitch circle, you get straight lines here, which is the way clock teeth are. They have straight slots. They don't have the curved slot. Okay. This is a graphic of how clock teeth work. Notice square bottoms. And you'll notice, can you click just on this bar? And hit the play again. Notice how much of it, you see that there's only one tooth touching. For a good part of the time, about roughly half the time, I think, there's only one tooth touching at a time. You only have the friction of this one tooth rubbing against the other one, and they slide. An involute doesn't slide. They mesh, but they don't really slide. I read a paper about they put a piece of paper in the corner of the wheel, and they ran a test to see, does the paper slide out? And in an involute case, it was imperceptible. With a epicycloid, clock gears, it slid right out. Well, yeah, they're sliding gears. That's what they're made for. As you see, there's two teeth. And now we're getting ready to lose the bottom one. There we go. We've separated from the bottom one. And now we're coming up onto the top tooth. There it is. I mean, when you think about this, I mean, these things have been going for hundreds of years. There's some pretty smart cats who came up with this stuff. We think of, oh, well, we've got CNC machines and we've got this and we've got laser. They did that without all of this stuff. It's pretty darn amazing. And one way that they reduce the friction is they have dissimilar metals. When you look at your clocks, your pinions are usually steel and your wheels are usually brass. You don't see brass on brass, you don't see steel on steel. You see brass on steel, even if you're doing lantern pinions. The lanterns, yeah, the outsides of the lanterns are brass, but the pins are steel. That reduces friction because the similar metals don't have a molecular bonding, which would make it sticky. Okay. Yep. Now for the finally timely item. Ready? Time's up. There's a song that says every new beginning comes from some other beginning's end. You're getting ready to have a new beginning because this beginning is ending. All right, very good.